today we're going to talk about the future of the universe. Now, the division of labor is that I'm going to start out by describing the physical universe, and then Lawrence will follow up with what's going to happen to biology and life in the face of this future. Now, before I do that, I want to define for you what I call a Copernican time principle. Now, you realized from hundreds of years ago that our Earth does not lie at the center of the solar system, but rather the sun does. And then ever since that time, astronomers have continually degraded our significance in some sense, right? Because we now know that we don't live at the center of our solar system doesn't live at the center of the galaxy, our galaxy does not live in a particularly important place in the universe is said to be homogeneous and isotropic. That means it's the same everywhere in space, it looks the same in all directions. So, in some sense, you're just not that special. Now, what I want to suggest today is that when you look at the physical universe, that same kind of principle holds in the time domain, namely that our current cosmological epoch, when viewed from a physical point of view, doesn't really have any special significance. And what I mean by that more specifically is that no matter how far into the future you look, interesting energy and entropy generating events will still happen just about as far into the future as you dare to imagine. So in order to do that, we need to define a new time variable for you. What's shown here is I'm going to write the time in years as 10 to some power, and the index, which we call the cosmological decade, will be a measure of time. So this is just a logarithmic time unit. Now, the one number you need to keep in mind throughout this discussion is that the current age of the universe is 13.7 billion years. Okay? Now, it's kind of remarkable that we can quote that to three significant figures with a straight face, right? But nonetheless, for today, we're going to step it back, and we're only going to talk about orders of magnitude. So I'll round 13 billion years to 10, which means that the universe is now 10 to the 10 years old. We live in the 10th cosmological decade. When the universe is 10 times older, 10 to the 11 years old, we'll be in the 11th cosmological decade, and so on. And I'm going to take you through a timeline here this morning that goes up to about 100 cosmological decades. So one of the remarkable things about modern physics and astrophysics and cosmology is that we have a timeline for the past history of the universe beginning at a Big Bang event, which we now know happens 13.7 billion years ago, all the way up to the present. So what we want to do is we want to take all of the physics and all of the astronomy that we learned to construct this timeline and carry that into the future and see what happens next. So here's a broad general outline of the entire history of the universe from start to finish. And you can divide this up into 5 eras as shown here. Now for the first million years, that means before cosmological decade 6, there were no stellar-like bodies of any kind, and the universe was a very different place. And that's called the primordial era. Right now we live in what's called the stelliferous era. Stelliferous means filled with stars. If you look out in the sky at night, what do you see? Well, you see stars. And if you look at galaxies, well, you're actually looking at the starlight from the galaxies when you see the galaxies. So even extragalactic astronomers are looking at stars. In fact, stars are generating most of the energy that's being generated in the universe today. So we live in this very bright epoch called the stelliferous era. It began when the universe was about 1 million years old at cosmological decade 6. Remember, now we're at cosmological decade 10, logarithmically right in the middle of this decade. But in linear time, we're very close to the beginning. And then this will continue up until around cosmological decade 14, when all the stars burn out and the universe becomes a very different place. At that time, we enter into the third era, which is called the degenerate era. Now here, degenerate doesn't refer to a moral statement about the universe, but rather when the stars burn out, they become degenerate objects, where in this case, degenerate means they're cold and dense, and they're supported by quantum mechanical degeneracy pressure. So the actual waviness of the stars is what holds them up, and that's why this era is degenerate. So the degenerate bodies will inherit the universe at cosmological decade 14 or so, and continue up until cosmological decade 40. At that time, even they will go away, and we'll see why in a minute, but at that point, black holes will be the only stellar-like bodies left. Now, one of the interesting things about this future timeline is that you usually define a black hole by saying something like, it's so dense and its gravity is so powerful that not even light can escape its surface. That's sort of a standard definition of a black hole. Well, at this point in our future The black holes will be the brightest things in the sky. And they will shine ever so faintly by a process called Hawking radiation. You may have heard of this guy, Stephen Hawking. And the reason why he's so famous is that he realized that if you wait long enough, even black holes will lose their energy, and they will do this through the Hawking mechanism. And at the end of this lecture, I will tell you how that works. So you too will know why Stephen Hawking is famous. And believe it or not, if you can keep three things in your head at the same time, and we have enough time here, you can understand that. And then after the black holes are gone, you see, in order for them to lose energy, they have to go away. And that happens on a time scale of about 100 cosmological decades. So after 100 cosmological decades, we're kind of done in the sense that all the stellar-like bodies ever formed are now gone. So it's kind of ashes to ashes, dust to dust, or in the case of the universe, more like particles at the early universe to just particles at the end of the universe. So that's the entire history of the universe there in one slide. What I'm going to do now is simply take you through that story and fill in some of the detail. Since time is short and you only get an hour of me, we're only going to go through some of the highlights. There's quite a lot more that we've established and worked on to understand this rich future. Now, to start with, we're going to go back to the beginning. So it's kind of sensible to ask, well, if the universe is 13.7 billion years old, what was there 15 billion years ago? What does that mean? Well, people always ask me that, so I have to have an answer. Now, this answer you won't find particularly satisfying, but I will nonetheless give you an answer. And the answer is that before there was a universe, there was, are you ready for this? There was a high-energy fluctuating space-time that changes its geometry every 10 to the minus 43 seconds or so. Okay? So there's this high-energy space-time, and it's fluctuating and it's frothy and foamy, and then every once in a while, some little patch of that space-time gets together and decides to expand exponentially. Now, you might say, like one of those Gary Larson cartoons, I'm being a little bit vague at that step. But that step is purposely vague because that is exactly where the frontiers of physics lie. That's exactly where we no longer have a particularly good theory that makes hard and fast predictions, although half of the physics community is working on that. It's just that that's what they're working on, so it's not done yet. That's why you call it research. But what's amazing is that after that point, 10 to the minus 43 seconds or so into the story, we actually know what happens next. So for the next 10 to the minus 37 seconds, the universe expands really, really fast, which makes the universe big, old, flat, and homogeneous. It also gets rid of magnetic monopoles, but we don't care about that today. And then something very interesting happens in the first microsecond. So since physics is an experimental science, I want you to reach out and touch the shoulder of the person next to you or behind you. Okay. Do the experiment. Now, none of you exploded, right? You saw that. So the experiment shows that the person next to you is made of matter, just like you are, rather than antimatter. There's this asymmetry in the universe, because astronomers have done this experiment, not just in this room, when we landed on the moon, and yes, we really did land on the moon. The astronauts didn't explode, right? So that means we're pretty sure that the moon is made of matter and not antimatter. And again, you can do this more indirectly all the way across the universe. And all of the data we have, all I can say is that all the data we have suggests that there are no anti-galaxies, there are no antimatter domains. All of the observable universe from here out to 15 billion light years away is all matter. And the question is, how did that come about? Well, again, we don't know exactly, but we know two things. We know that some version of the laws of physics must allow for an asymmetry between matter and antimatter, or more precisely for today's talk, there must be a way to convert one into the other. Because somehow the universe decided to make a little more matter than antimatter. Now, the asymmetry is not as big as you think, because back in this time, when the universe is only a microsecond old, most of the matter is in the form of quarks, which are the constituent particles of the regular matter that you know about. And the asymmetry is small. So for every 30 million antiquarks, there were 30 million and one regular quarks. So what happens is that the 30 million quarks annihilate with 30 million antiquarks. The one regular quark left over is left over to get confined into protons and neutrons, the stuff of ordinary matter that you make, or that you know about. Now, the reason why this is important is it will come back. It means nothing less than the fact that everything in the universe is doomed. And what that means is that because there's a channel that will allow matter to turn into antimatter, that means there's a channel for protons to decay. So that since everything that you care about in the universe, like stars and planets and people, are made of baryons, or protons and neutrons, we know that if you wait long enough, they will decay, which means that there's a finite lifetime to the phase of the universe we live in now. And we'll come back to that in a little bit. But to continue my story, after about 1 microsecond, we form the protons and neutrons. After 1 second, the dark matter particles freeze out. And after 3 minutes, a large fraction of the protons and neutrons get together to form helium. Now, it turns out that 1/4 of the mass of the entire universe is converted from hydrogen to helium in a 3-minute time window. Now you might think, well, how do we know this? Because we know that stars produce helium also. But the amount of helium produced in this 3-minute window is about 10 times more than all the helium produced in all the stars, in all the galaxies, in all the universe over all of time. In other words, this was a serious nuclear explosion that was going on for 3 minutes because it produced 10 times more helium than all the stars have ever done. And that's one of the interesting things that lets us understand the past history of the universe with some detail. And that gives us some feeling for what happens next. Here we see that we get not only the right amount of helium out of Big Bang nucleosynthesis, as it's called, but also the right amount of deuterium and lithium and other light elements. And that takes us to the end of the primordial era. This was just an introduction. We start at the Big Bang where things are very fuzzy, and then for 10 to the minus 37 seconds, we expand very rapidly. At 1 microsecond, we turn some matter, or we have some asymmetry between matter and antimatter. The quarks get confined to protons and neutrons, and then we form all this helium. And while all this is happening, the universe continues to expand. So we see the signature of this early phase in the microwave background, which was set up, and this is real data, a real picture of the universe, which tells us what was happening when the universe was only 300,000 years old. And then out of that, you form structures. This is a simulation halfway across the universe. And then inside that, you see all the usual structures that you've seen. And that takes us up to the present time. So what I want to do now is take you through the future history of the universe. So from this point on, we're going deeper and deeper into the future. This was a whirlwind tour of how we got from the Big Bang to today. So now the universe is 13.7 billion years old, and we're just going to keep going. Now, one of the things that we've realized in the last decade, really, is that the universe is accelerating, and we've actually finally been able to pin down the content of the universe. So we know that the universe contains about 30% matter and 70% other stuff, which we call dark energy, which causes the universe to accelerate. And of the dark matter, we know about 1/6 of it, or of the matter, we know about 1/6 of it is regular baryonic matter, the protons and neutrons we talked about. And the rest of it is a different kind of matter called dark matter, which doesn't interact very strongly. Given that we finally figured out what the basic parameters of the universe are, we can now take cosmological simulations and run them into the future. And that's what's shown here. So that's sort of a poor man's movie with only 3 frames in it. What we've done is we started at the very beginning and run a computer simulation to the present day. And that gives us the large-scale structure that we see today. And that's shown in the top panel. And then what we did next was we simply did nothing. In other words, we were too lazy to turn off the computer. So we just let it run to see what would happen as we go into the future. But because the universe is accelerating, the frame on the top, or this small frame in the large frame on the top, becomes the middle frame, and then the small frame here becomes the bottom frame. And if you look closely, you see that the only thing left in a horizon in the far future, well, the far future isn't that far, it's only about 10 times older than the universe is now, is that you get one single galaxy, or one single halo of a galaxy, being its own island universe. So this is the fate of all of the large-scale structure in the universe, that every particular structure that's bound today will be accelerated away from every other bound structure, and that at the end, The only thing you'll not only be bound to, but the only thing you can actually see in the universe will be the things that are gravitationally bound. Now, in the case of our Milky Way, we live in this Milky Way galaxy, we have a friend, and her name is Andromeda, and the Milky Way and Andromeda are the only two big galaxies that are bound to this local structure that we live in called the local group. And here's a picture of Andromeda. So if we wait, in this case, 10 billion years, the only thing that Milky Way will be bound to is Andromeda. But over that time, something else happens that's even more interesting. Because if you look closely at Andromeda, what you find, you can't tell it from this picture, but it's actually headed straight for us. So if you wait not the 92 billion years it takes for us to be isolated, but rather only about another 10 billion years, then what happens is that the Milky Way and Andromeda will collide with each other and become one great big galaxy. Now this is kind of interesting. When you look at galaxies colliding, if you look at them from the outside, those beautiful spiral patterns like the one I showed you here goes away, and you rip these streamers of stars and gas out of them, and colliding galaxies, when viewed from the outside, look like this train wreck. But now let's take ourselves inside the galaxy and ask what that looks like. Well, you might not realize it, but galaxies are almost relentlessly empty. So if you shrink stars down to the size of grains of sand, then there's miles and miles of space in between those grains of sand. So imagine that you send your friend a few miles away holding a grain of sand, and you try to throw it at him. The chances of hitting it are small. In very much the same way, when Milky Way and Andromeda collide, the chances of any two stars in the field actually hitting each other is pretty small. So if you could live for billions of years and see this collision take place from within, all you would see is a gradual doubling of the brightness of the night sky. Now let's take ourselves a little closer to home and ask, what is the fate of our sun? The sun is our friendly neighborhood star, of course. And the way we study stars is we plot them in what's called the Hertzsprung-Russell diagram, which is just a fancy way of saying we plot the power output on the vertical axis and the temperature, or spectral class, or the color on the horizontal axis. And temperature increases backwards in keeping with astronomical traditions. So for any given star at any given time, you can plot its power output and its temperature and then see where it is in its life. And the interesting thing about stellar structure is that stars go through well-defined gyrations in this diagram as they live and die. So stars of different mass are born on this main sequence, and then as they die, they do what I'm going to describe next. So right now the sun is at point A, where it has a power of 1, which is sort of a coincidence. Well, it's not really a coincidence because we measure it in units of the sun's power output. So right now it's actually at 1. But if you wait just 3.5 billion years, it goes from point A to point B. Now from your viewpoint in the audience, it doesn't look like a very dramatic event to go from point A to point B, which is 3.5 billion years from now. But it might matter in that that marks the end of life on Earth. What happens when the sun becomes just this much brighter is it's able to run or to drive a runaway greenhouse effect. Not just the global warming that's happening on a century time scale, but enough to sterilize the biosphere completely. So if nothing else happens, that point B, 3.5 billion years from now, marks the end of life on the planet. But if you're the Earth, you don't really care about the biosphere because it's just this little crusty layer on the outside. The planet's just fine at that point. But as the sun gets brighter, it goes all the way up to point C, where you see that it's 10,000 times brighter than it is now. So what happens is that the sun gets brighter, it gets a little cooler, but it gets physically larger. So the sun's photosphere, its outer boundary, will first overtake Mercury, and then Venus, and then it will come out to about the radius where Earth's orbit is now. Now, since the sun loses a lot of mass as it's doing this, the Earth's orbit gets a little bit larger. So it seemingly would escape. However, because the sun is losing mass, the Earth has to plow through that stuff, and that causes friction, which drags it back in. So if you wait long enough, as shown in this picture, just schematically, the Earth will be swallowed by the sun in about 7 billion years' time. So there's a nice... 7 billion, yes. Not million, but billion. You got time, okay? It won't affect your real estate investments. So. Now that's if nothing else happens. So there's a way to save the Earth. It's possible that nearby stars will come close enough to the solar system to scatter the Earth out of its orbit. And most stars are small. Most stars are much smaller than the sun, and we call them red dwarfs. Okay, they don't really look like this picture, but what's amazing is that we can calculate in detail what the scattering interactions are between passing stars in our solar system. And we know the density of stars, and we know the speed of the stars, and so on and so forth. So we can calculate the odds of this happening with some precision. So if we look at a given time frame, the 3.5 billion years that we have left in our biosphere, the chances of saving the Earth are about 1 part in 10 to the 5. Now, that's not real good odds, but it's actually about 30 times greater odds than the odds of you winning the lottery. Now, people buy lottery tickets, so you got to wonder. Now, you might ask, well, what good does this do? I mean, Earth is scattered out of the solar system in this scenario, but what good does that do for life? Well, it turns out that icy worlds are easy to make. What happens is that the oceans will freeze, but not all the way down. Well, they'll freeze only about 14 kilometers down. Now, that's a problem because the oceans are only about 4 kilometers deep. But any water that lives deep underground, with more than 14 kilometers deep underground, will still remain in liquid form. So life in little pockets can live longer, actually, if the Earth is scattered out of the solar system than if it stays. But the reason why that's interesting is that if you take that concept and you apply it globally across the galaxy, like I said moments ago, icy worlds are easy to make. So if you make an Earth-like planet in the outer solar system of some solar system, not ours, it will naturally have more than 14 kilometers of ice on it. The icy Galilean satellites typically have 100 kilometers of ice on them. So if you put these pieces together, what you find is that if you have an Earth, and it has 100 kilometers of ice on it, not our Earth, but a different one, then there'll be a layer of liquid water 14 kilometers down. Now, the power source for this is the internal radioactivity of the planet, which is about 10,000 times less than the external radiation we get from the sun in the case of Earth. But if you are in the frozen realms, or if you scatter the Earth out of the solar system, that's all you get. So that becomes the most important power source. And the reason why this is important is that it means that these are the most common liquid water environments in the galaxy. So these very well may be the most common places for life to exist. Now, some have even suggested that life on Earth originates deep underground, so it's possible that on these frozen planets, the same kind of thing could happen. Now, of course, the real big game lottery winner is not to scatter the Earth out of the solar system, but rather to capture the Earth. And we can calculate the odds of that happening too, and they occur through very, very messy, interesting, chaotic scattering events. But the odds of this happening are a bit lower, about 1 in 3 million over the course of time that the biosphere has left. Now, if we go to slightly longer timescales, we can ask, how long does the galaxy continue to make new stars? We've kind of seen what happens to the life cycle of our own sun. Well, to make a long story short, the galaxy goes through this, what I call a karmic cycle of evolution, where molecular clouds turn into stars, and stars return some of their material back into the interstellar medium by winds and by blowing up. But if you wait long enough, this cycle will grind to a halt because the galaxy will literally run out of gas. Now, the longest an ordinary galaxy like the Milky Way can continue to sustain ordinary star formation is approximately 10 to 100 billion years. No, trillion years, excuse me. So 13 or 14 cosmological decades. Now, I should remark that most of the star formation that is going to happen will happen sooner than that. That's just the longest possible extension that you can make new stars. So, as shown here, the star formation continues in the galaxy until it literally runs out of gas at cosmological decade 14 or so. And then you can ask the question, well, Okay, so we can make new stars up to cosmological decade 14. What about the stars that we have? Well, the biggest stars live for only tens of millions of years, so they will be long gone on this time scale. As we've already seen, stars like the Sun live for about 10 billion years, about a time scale comparable to the current age of the universe. But what's shown here is the lifetimes of the smallest stars. So in this little inset diagram, we're plotting the lifetime of the smallest stars as a function of mass. And for ordinary metal content, the longest lived star lives for 12 trillion years. If you project into the future, since the galaxy produces more heavy metals as it gets older, and the heavy metals make the stars live longer, the longest lived stars can live for tens of trillions of years, which is also 13 or 14 cosmological decades. So we have a little bit of a coincidence in that the longest lived stars and the timescale over which galaxies can continue to make stars are both about 13 cosmological decades or so that by the time you get to cosmological decade 14, when the universe is 100 trillion years old, you're pretty much out of business, and the stelliferous era comes to an end. So, to cut to the chase, we see that during the stelliferous era, the stars are dominating our energy production, and the lowest mass stars are the ones that are not dying, because all the bigger ones go away. So the lowest mass stars become increasingly important as the universe gets older and older. In fact, because the smallest stars are the only ones survive, and since they tend to get brighter, all stars tend to get brighter as they get older, even though the bigger stars are dying off, the overall power output of a galaxy doesn't actually change that much until we reach this point where all the little stars are dying and we can make no more new big stars. So the power output of the universe is relatively constant up to about cosmological decade 13 or so, and then it has a sharp cutoff and we enter into the next era, which of course is the degenerate era. So at this point, let's step back and take inventory of what we have left. Remember, now the universe is 10 to the 14 years old at this point. All the regular stars have gone, and they've gone in the sense that they've run their course of stellar evolution, and they're no longer generating energy through ordinary hydrogen burning. So the most energetic process that runs our universe today is now over. So what do we have left? Well, about half the objects are in the form of brown dwarfs. Now, brown dwarfs are stars that aren't really stars. They're just stellar-like bodies that are very small. They're small in mass with less than 8% of the mass of the Sun. And they're so small that they don't have enough mass to burn hydrogen. So what they've done for the intervening 10 to the 14 years is basically nothing. They're kind of like the ultimate stellar slackers. They've sat around for half of eternity now and still haven't done anything. Now, they turn out to be important because they contain unburned hydrogen gas, and we'll see how that plays out in a moment. Now, most stars, those between 8% of the mass of the Sun and 8 times the mass of the Sun, that's 997 out of 1,000 of all stars, they will turn into white dwarfs upon their death, where you take a star with the mass of the star, like the Sun, and it shrinks down to a radial extent about the size of the Earth. And at that point, the electrons in the system are so close together that they push on each other through quantum mechanics, and that's why it's a degenerate object, but that degeneracy pressure keeps it from shrinking further. Now, the very most massive stars, those bigger than 8 times the mass of the Sun, explode at the end of their lifetimes, so they die in much more dramatic fashion. And some fraction of those turn into neutron stars, and some fraction of those turn into black holes. Neutron stars are also degenerate objects, except in this case, we've shrunk a stellar-like body down to the size of about 10 kilometers, the size of a small city. And at that point, it's at nuclear density. So a neutron star is really like one big atomic nucleus, about a quadrillion times denser than an ordinary star, about a quadrillion times denser than water or you. So that's what we have to work with. If you show the inventory by a pie chart, you see that by number there's almost as many brown dwarfs as white dwarfs, somewhat fewer, but by mass, the white dwarfs are 10 times heavier, so all of the mass that used to be in stars is now in the white dwarfs. Now, I told you that star formation came to an end, and I told you that stellar collisions just didn't happen. And in both cases, I actually lied to you, because if you wait long enough, rare events do happen. So once the universe becomes old enough to be in the degenerate era, brown dwarfs will begin to collide. Now think about it. We know the number of brown dwarfs. We know roughly what orbits are on. We can calculate what cross-section we need, how close they have to come in order to collide. Once they collide, what they form is a bigger body. Since most brown dwarfs are just a little bit too small to burn hydrogen, when you bash two of them together, you get something that is big enough to burn hydrogen. And it will typically be a very small star. And we've also seen that we now know what the lifetimes of the smallest stars are. So when you put all these pieces together, you can figure out how many stars will be shining during the degenerate era. Now remember, today, in a galaxy like the Milky Way, there's billions and billions of stars, as Carl Sagan has taught us. So instead of billions and billions of stars, there will be one or two stars that are formed through this process of brown dwarf collision. Now, just like the brown dwarfs will collide, the white dwarfs will occasionally collide as well at about the same rate, but usually when two white dwarfs collide, you just get a funny white dwarf, and nothing particularly important happens. But when two very large white dwarfs collide, you get a supernova explosion. So this dark future that our galaxy is going to face will have one or two ordinary really dim stars, typically about 1,000 times dimmer than the sun. And then every once in a while, this dark future will be punctuated by this spectacular supernova explosion from white dwarf collisions. But the white dwarfs do something else. Remember that most of the matter is not ordinary baryons, protons and neutrons, but rather this strange dark matter stuff that doesn't interact very strongly. Well, if you wait these kinds of timescales, the white dwarfs will hoover up dark matter particles and they'll collect in their centers. And the annihilation of those dark matter particles in the centers will provide them with a power source. And that power source will be quadrillions of watts. To put that in perspective, that's approximately the same amount of power that the Earth intercepts from the sun. So each white dwarf, and there will be billions and billions of them, because remember we started with billions of stars, and they will turn into these billions of white dwarfs. So each of those billions of white dwarfs will have a power of several quadrillion watts. And that will be an important power source in this future. Now, just like stars will collide occasionally, even more often they will come near each other and not collide. Now, that has important consequences on an even longer time scale, because as stars go near each other and don't collide, what they do is they change their trajectories a little bit, they share energy, and that means that some stars will get kicked up to large energy. That's a process of evaporation. And essentially, it's the same thing that happens in water, right? If you leave a glass of water out long enough for a few days, it goes away. And the reason why it goes away is some water molecules get kicked up to high energy and they leave and they go off into the air and they're done. Well, what happens to our galaxy is if you wait long enough, the stars get kicked up to a high energy and they leave the system and the system dwindles. And that takes on the order of 20 cosmological decades. Now we're running a little lower on time, so I'm going to have to speed up, but that's okay. So I'm going to now jump from cosmological decade 20 to cosmological decades in the 30s, and I'm being purposely vague here, because what happens next is that most of the ordinary matter is in the form of either gas between stars or confined to these white dwarfs, and we want to know what happens to them. Well, what happens to them, as we said earlier in the lecture, that their protons, their constituent protons, will decay if you wait long enough. Now, there's one problem with this whole story, is that the lifetime is not known. In fact, it's very uncertain. But this is, in fact, in experimental science. We've set firm lower limits so that we know that the protons live longer than about 10 to the 33 years. And there's fairly compelling theoretical reasons to think that they don't live longer than 10 to the 45 years. So the proton decay lifetime is probably confined to be between 33 or so and 45 cosmological decades. So we really need to pin down this number more, but modulo the uncertainty in the lifetime, we can say what happens next. And to emphasize this to you, this process will probably change the universe more dramatically than just about anything else that we're talking about today. So just to give you some idea of how the proton can decay, we look at its constituent particles, which are quarks. And to think about it, two of the quarks get together and produce a positron and an antiquark. And that's one of the many channels that can allow a proton to decay. If this process happens inside a white dwarf, the positron annihilates with an electron, and then the pion, which is a quark and an antiquark, decays into radiation. So the net effect is that you've turned all the mass energy of the proton into radiation, and then that leaks out of the star. And then we can put the stars in a Hertzsprung-Russell diagram, much like the one I showed you earlier, where I'm plotting the power on the vertical axis and the temperature on the horizontal axis, again plotted backwards. But in this case, this is still in solar units, but now it's at 10 to the minus 5. Oh, no, this isn't in solar units. This is in watts. But so these are very, very low numbers compared to the ones I showed you. But as a white dwarf gets loses its mass, it gets physically larger. Remember, it started with the mass of the sun, more or less, and the size of the Earth. And then it grows until it's the mass of Jupiter, which is 1,000 times smaller, and the radius of Jupiter, which is 10 times bigger. And then at this point in its lifetime, it's just this block of hydrogen ice. And then it slowly decays away into nothingness, as shown here. And that's the fate of not only our sun, but of almost every star in the sky. And that takes us to the end of the degenerate era, where we have this inventory of brown dwarfs, white dwarfs, neutron stars, and black holes. And one of the things I want to leave you with is that lots of interesting things keep happening, right? There's continuous star formation through brown dwarf collisions. The white dwarfs eat dark matter particles and annihilate them and have a power source through that process. The galaxy evaporates. And all the time, the black holes get bigger and bigger because they'll eat anything that comes too close. So if we wait till we're at cosmological decade 40 or 50 now, the only stellar-like bodies left are black holes. So let's take a moment and take inventory. So each galaxy, each major galaxy like the Milky Way or Andromeda, produces one supermassive black hole in its center with a mass about of anywhere from 1 million to 1 billion times the mass of the sun. And then in addition, from supernovae explosions, we get stellar black holes with typical masses about 10 times that of the sun. And there will be about 1 million of those per big galaxy. So these are all the bodies you have left at this time in the future. About one supermassive black hole and about 1 million smaller stellar mass black holes for each big galaxy. And then you can ask, well, what do? Well, what they do is they shine through this process of Hawking radiation. So let me try to explain to you exactly how that works. So the first step of the explanation is the following. There's something called a tidal force. If you just stand on the Earth like we are here, we know that the amount that the Earth is pulling on you depends on how far you are away from its center. So if you think about that, your feet are closer to the center of the Earth than your head. So you're being stretched by the tidal forces of the Earth. Now, for Earth is a pretty wimpy object, gravitationally speaking, so it doesn't actually have any visible effect. You can't really feel your head popping off or anything dramatic like that. But if you were near the surface of a black hole, which is all about extreme gravity, these tidal forces would be enormous. Okay, so hold that thought. We have these tidal stretching forces going on, and near the event horizon of a black hole, they're enormous. Now let's put in quantum mechanics. Well, quantum mechanics tells us a lot of things. In particular, it tells us about an uncertainty principle, which allows energy to be violated, conservation of energy to be violated for a small amount of time. What that effectively means is that little particles, which I've drawn here with PowerPoint arrows, they can come out of empty space and then annihilate a short time later. And this is not even allowed, but in some sense required by quantum mechanics. And these are not just made-up particles. They're virtual particles in the sense that they don't live for very long. But they're real in the sense that these virtual particles interact with things in accelerators. So if you go over to Fermilab and look at the experimental data that they get, the interactions of these virtual particles with the real particles they make in the accelerator are things that are measurable by physicists. So this isn't just a story. This is something that's verified, gazillions of times each time they run the experiment. But let's suppose that we have these virtual particles popping in and out of existence near the surface of a black hole. So while they're in existence, we'll go back to our tidal force. The tidal force is acting on them. So now you need the third bit of the explanation, namely that work is force times distance, which you might have learned in freshman physics sometime. In other words, if you push on something for a while, you do work on it, which means you give it energy. If you push on a box, you give it energy, you make it go. If a tidal force stretches the virtual particles, it gives them energy. It does work on them. So suppose it does enough work on them to promote a virtual particle from virtual existence to real existence. That means that the particle doesn't have to go away anymore. It doesn't have to disappear into the vacuum. It can fly off into space. So that's how Hawking radiation works. The tidal forces act on virtual particles, do work on them, promote them to real existence. The particle goes away. Now something has to pay for it. You don't get something for nothing. Well, what's doing the work is the gravitational force. The gravitational force has a source in the mass of the black hole. So the mass of the black hole has to pay for this expenditure by getting smaller. So the emission of radiation by a black hole means that the black holes are getting smaller with time. Now it turns out it takes a long time. If you go through the equations, it takes 10 to the 65 years, or 65 cosmological decades, for a one solar mass star, or one solar mass black hole to evaporate. And then we can now account for the entire black hole era, because we have 1 million stellar black holes with masses anywhere from 1 sun to 10 suns. They will all go away in 65 to 68 cosmological decades. 1 million solar mass black hole, like the one in the middle of our galaxy, goes away in 83 cosmological decades. The largest black hole you can imagine making is for a black hole to eat most of the mass of a galaxy. And that kind of object will evaporate in only 98 cosmological decades. And just to show you that black holes are not forever, if you take every particle in the entire observable universe today and you ball that up into a black hole, that will evaporate in only 131 cosmological decades. So you can see that if you wait long enough, no matter how big a black hole you can plausibly make, the black hole era will come to an end, and we enter into this fifth and final era called the dark era, where, as my colleague said on TV once, it will be very, very dark. And the reason why it will be very, very dark is that there are no stellar bodies of any kind left. All we have are the particles left over from all of the processes that I talked about today. Occasionally electrons and positrons will get together, but not very often, and then you'll get these little tiny bursts of radiation. But in the spirit of never say never, there's a lot of more speculative things that could happen. One that could happen is shown here. I showed you earlier that the universe is now accelerating. In order for the universe to accelerate, that means that empty space has to have some energy associated with it, or that's how we think it works. That's sort of a mysterious concept that we can talk about later, but for now, just go with it. So if we have empty space having an energy associated with it, why not let it have two energy levels associated with it? That's actually not a whole lot more implausible. And if that's the case, then empty space has two energy levels associated with it, and it's now in a high energy state, shown schematically here, and that's allowing the universe to accelerate. Then if there's a lower energy state accessible, that means that the universe could make a transition from the high energy state to the low energy state, thereby going through a phase transition. So I drew you a picture of that. It's shown here. What happens is that a little tiny bit of space will make this transition from the old state, the dark blue, to the new state, the light blue, where it has this new lower energy state. And then what happens is that the bubbles grow, and then the phase transition completes. Now, the reason why this might be important is that in order for the phase transition to take place, there has to be some field associated with that transition, and that field can talk to the other particles and the laws of nature. In other words, this transition can affect, in principle, the strength of the forces and the masses of the particles that describe the laws of physics. So in short, it's possible that the laws of physics would change when this phase transition, if this phase transition were to occur. Now, I need to emphasize here, we're getting a little bit speculative, and we're 10 to the 100 years into the future. But these are the kinds of things that physicists are now working on. We want to know exactly how it is that the masses of the particles get produced, and how it is that the law or the strengths of the different forces get determined. And once we understand that, we can say with some certainty whether or not this kind of scenario would happen. But my point is simply that you can take the future this far into the future and even when you seemingly have run out of things to do, there's still interesting physical processes that can happen. And I think this is a good place to stop. And thank you for your attention.